Okay, rest of lesson 25. Doesn't seem like it's quite as related to that hydrogen as it really is. But those hydrogens, being acidic, are very important really from this point on through the rest of the semester. So, when we're looking at the alpha carbon position, note that these guys have very specific reactivity. And you can add a Cl2 here, or better yet, substitute a Cl for a hydrogen in acidic conditions. Now, interestingly enough, we only get one chlorine at the alpha position if we're using acid. But if we use a base, then we actually get two, or better yet, as many as possible on that alpha position. And these work with bromine, chlorine, or even iodine in this case. And it's not even explosive. Isn't that cool? Okay. So let's look at the acid catalyzed mechanism first. In the acid catalyzed mechanism, the oxygen comes and grabs the hydrogen, just like we've seen a million times. This water grabs the hydrogen and electrons go back to this bond, pushing that guy now up. This looks relatively stable, except for the fact that that's now an enol form, which is not the most stable form. So these electrons pull down, and when these come back down, they can't find the water as easily, but they certainly can find a chlorine, and away go the electrons. Why is that necessarily the case? Because chlorine can just be grabbed more easily than a hydrogen will come off of an acid for sure, but water in general. Water will then go and pick up a hydrogen, and there we go. We end up getting one chlorine on there. Now, at this point, you've got chlorine next door that's pulling electron density away from this oxygen, right? So that oxygen is less likely to go and grab a hydrogen from another acid molecule than it would be if that chlorine was not there. And as a matter of fact, it's so much less reactive, it just stops. So we only get one chlorine that's attaching there. Okay, well now let's look at the base catalyzed version. With the base catalyzed version, we've got a acidic alpha hydrogen. Ooh, does that sound familiar? So the oxygen, or the OH, comes and grabs that hydrogen. Electrons go back to that carbon. Well, resonance happens again. We have electrons come in and up, and this looks familiar, hopefully, because as that enol type of thing forms, it comes down, and bam, we end up getting that chlorine off, and that leaves. Well, now, here's your first chlorine there. Unlike the acid catalyzed, what you now have is you have more electron withdrawing groups around where this hydrogen is, right? Because there's still another hydrogen here. Chlorine's pulling electrons back that way, pulling electrons up this way towards the oxygen, which means that this hydrogen that's over here, even though it's not written, obviously, that's actually going to be more acidic. So the next base that can come over is going to grab another hydrogen. And when it does that, bam! You're going to get more chlorine attached, not less. And that's the reason why in one set of conditions you can end up with one chlorine, and with the other you end up with only as many chlorines as possible. If this was not here, if this was just a CH3, you could actually end up getting a Cl3. Excuse me, if it was a CH3 over here, then you could end up getting a Cl3 over here. Okay. Well, you could also do a bromination of carboxylic acids at the alpha position. This is a really kind of strange reaction because it's not what at least I would envision. Because PBr3, okay, great, that should react with the OH, right? Well, sort of. Okay, so carboxylic acid, you can actually put a bromine at the alpha position. Note that we were not doing a carboxylic acid before. We were talking about aldehydes and ketones, right? Well, in a carboxylic acid with PBr3, you're right that OH gets replaced with that Br. Well, this guy can go through the enol form, right? And when it does, electrons come down and grab that bromine. Okay, it's kind of just like their last reaction. And you end up with this. That is kind of nasty looking, right? Well, as these electrons then come down, this bromine gets replaced by that water. Why? Why doesn't this one get replaced by that water? Remember how we talked about carboxylic acid derivatives, right? Well, instead of this being an acyl chloride, this is an acyl bromide. An acyl bromide with water around, bam, that guy's going to come in and replace that, right? Okay, so that's exactly what's going to go on there. You need to be careful when you're replacing halogens. If you have a really strong base, you can actually end up with a whole bunch of mixture of problems, and specifically you can get some enolate ions, which we're going to talk about what that even is next lesson, so don't worry about that too much. But like weak bases, carboxylates, things like this can actually replace that. So be careful if you're just trying to replace that bromine with like an OH. That won't work here. Okay? Okay, thank you very much.